Good morning to everyone. In this video, we have going to see about the truss problems. So, concerning the three-bar truss as shown in figure. So here they're having a three trusses. The Young's modulus of the elements will be an 2 into 10 to the power 5 Newton per mm square. Area of each elements for element 1 2000 mm square, for element 2 2500 mm square, and element 3 2500 mm square. So they're having a three different cross sections. So the element 1 will be in 2000 and element 2, element 3 will be in same cross section of 2500 mm square. We need to calculate the nodal displacements of each elements and then stress out each elements and then reaction force for an each nodes. So the location of elements will be shown in the figure. The common distance of horizontal elements will be in 1000 mm and then vertical locations will be a height of 500 mm. The force is acting at the top of the element at a vertical direction for 50 kilonewton. And then constraints. The left hand constraint will be a hinge supports and then right hand constraint will be a roller supports. So these are the given from this problem. Based on this, we want to solve and find the nodal displacements and then stresses and reaction forces. So already they give it as this inclined member will be an element 1 and then the horizontal member will be an element 2 and this inclined member will be an element 3. The top point will be a node 1 and then left corner will be a node 2, right corner will be a node 3. Here the node 2 will be an hinged supports, so all the degrees of freedom will be free. In this, the node 3 they are having a roller support, only horizontal deformations will be available, vertical deformations will be 0. And the node 1 they are having a free support, so all the degrees of freedom will be free. And then external force, node 1 vertical force is 50 kilonewton. It will be converted into a Newton, means 50 into 10 to the power 3. That is called as an F2. F1, F3, F4, F5, F6 will be an 0. So that will be mentioning here. For node 1, node 2, node 3, the x coordinates will be an 500, 500. Because it will be considered as a center point. It will be considered as a right angle triangle. So for that, the vertical movements will be 500. The horizontal total distance will be 1000. So for that, we will consider as a center point 1000 divided by 2, 500. So node 1 coordinate point will be in 500, 500. Node 2, that is an initial point. So x will be 0, y will be 0. Node 3, the horizontal distance will be 1000, vertical distance will be 0. So x 1000, y 0. And then element connectivity. For element 1, connected with node of 1 and 2. Element 2 connected with a node of 2 and 3. Element 3 connected with node of 1 and 3. So these are the connectivity table. Now we want to find the element 1 stiffness matrix. So for that, we want to find the length of the elements. So based on the right angle triangle, if we want to find the hypotenuse side, so root of adjacent side square plus opposite side square. So for that, the opposite side adjacent side square will be an L2 divided by 2 square, and then the vertical distance will be an 0.5 square. So we will take it as we will give it as a meter, or we will consider as 500 square. So 500 square plus 500 square, the value will be an 707 mm. So length of L1 and L3, both the elements length will be an same. So that will be considered as 707 mm. And then length of element 2 will be given as 1000. So based on this equation, we can find the values of each element length. So thank you. We'll see you in next video. Good morning to everyone. In this video, we are going to continue the previous trust problem continuity. So previously we have discussed about the nodes, elements, and then force, constraint, and we can calculate the length of the elements. Now we going to calculate the direction conditions. So we can find the length of each element. So element 1 will be in 707.1 mm. Element 2 length will be in 1000 mm, and element 3 will be in 707.1 mm. Then we want to find the L1 M1 of the individual elements. So here by using of a formula of cos theta, or otherwise x2 minus x1 divided by Le1, or x3 minus x1 divided by Le1, or x1 minus x2 divided by Le1. So for that we can get as an L1 value will be an 0.707, and then L2 will be an 1, L3 will be an 0.7071. Based on that we want to find the M value. We'll take it as a sin theta, or otherwise y2 minus y1 divided by Le1. So here the value will be minus 0.7071, 0 minus 0.7071. Based on this we can find the element matrix. So K will be an AE divided by L based on the sign or terms, or otherwise L square Lm minus L square minus Lm, Lm M square minus Lm M square minus L square minus Lm, L square Lm minus L square, minus Lm minus M square, Lm M square. So already we know area of element 1 2000, and then Young's modulus 2 into 10 to the power 5, length of the element 1 707.1, and then L1 M1 value 0.25 square, and then 0.075, 0 minus 0.075. So we are applying that, we will get as an element 1 equation. Next we want to find the element 2 equations. So element 1 equations, after calculating the 2002 into 10 to the power 5 divided by length of 707, we have multiplied the internal terms. We will get as an 28.284 into 10 to the power 3, 28.284 into 10 to the power 3, minus 28.284 into 10 to the power 3, minus 28.284 into 10 to the power 3, 28.284 into 10 to the power 3, 28.284 into 10 to the power 3, minus 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 28.284 into 10 to the power 3, 28.284 into 10 to the power 3, and then 28.284 into 10 to the power 3, minus 28.284 into 10 to the power 3, minus 28.284 into 10 to the power 3, 28.284 into 10 to the power 3, 28.284 into 10 to the power 3. So this is the final equation of element 1. And then we are applying element 2. The area will be an 2500, Young's modulus 2 into 10 to the power 5, length will be an 1000, and then the value will be in 1 and 0. L value will be 1 and M value will be 0. So the matrix will be an 1 0 minus 1 0, 0 0 0 0, minus 1 0 1 0, 0 0 0. So we multiplying a 40 into 10 to the power 3. So 40 into 10 to the power 3 0, minus 40 into 10 to the power 3 0, and then 0 0 0 0, minus 40 into 10 to the power 3 0, 40 into 10 to the power 3 0, 0 0 0 0. Next, element 3 equations. We are applying a AE divided by L values. We will get as an A value will be in 2000, Young's modulus 2 into 10 to the power 5, L value will be in 717.6. So final value will be in 56.69 into 10 to the power 3. The matrix value will be in 0.5 minus 0.5 minus 0.5 0.5 minus 0.5 0.5 0.5 minus 0.5 minus 0.5 0.5 0.5 minus 0.5 0.5 minus 0.5 minus 0.5 0.5. So from this we can calculate the element equations of element 1, element 2, element 3. Then we want to assemble the global stiffness matrix. So before going to assemble the global stiffness matrix, we want to find the size of the elements. So here they are having a 3 nodes Each nodes having 2 deformations. So size will be an 6 cross 6. Okay, thank you. We will see you in next video. So finally, we are going to assemble the global stiffness matrix. Already previous two videos we can see about the how to apply the nodal conditions and constraints, then how to find the element stiffness matrix. Now we are going to assemble the stiffness matrix. So node 1 will be sharing for 2 elements, and node 2 will be sharing for 2 elements, and node 3 will be sharing for 2 elements. So the value of 1 comma 1 1 comma 2 2 comma 1 2 comma 2 for node 1, and node 2 3 comma 3 3 comma 4 4 comma 3 4 comma 4, and then node 3 5 comma 5 5 comma 6 6 comma 5 6 comma 6. It will be sharing for 2 elements, so they're having a 2 values. So for 1 comma 1 28.284 into 10 to the power 3, and then 28.28 into 10 to the power 3. Node to 28.28 into 10 to the power 3 minus 28 into 28 into 10 to the power 3, and then 3 1 comma 3 minus 28 into 28.28 into 10 to the power 3. 4 comma 1, so 1 comma 4 minus 28.28 into 10 to the power 3. 1 comma 5 minus 28 into 0.28 into 10 to the power 3. 1 comma 6 28.28 into 10 to the power 3. 2 comma 1, they're having two values, 28.284 into 10 to the power 3 minus 28.28 into 10 to the power 3. 2 comma 2, they're having a two values, one will be in 28.28 into 10 to the power 3, and then 28.28 into 10 to the power 3. Node 3 minus 28.28 into 10 to the power 3, and then 2 comma 4 minus 28.28 into 10 to the power 3. 2 comma 5 28.28 into 10 to the power 3. 2 comma 6 minus 28.28 into 10 to the power 3. 3 comma 1 minus 28.28 into 10 to the power 3. 3 comma 2 minus 28.28 into 10 to the power 3. 3 comma 3, they are having a two values, 28.28 into 10 to the power 3 plus 40 into 10 to the power 3, and then 3 comma 4, they are having a two values, 28.28 into 10 to the power 3 plus 0. 3 comma 5 minus 40 into 10 to the power 3, 3 comma 6 0. 4 comma 1 minus 28.28 into 10 to the power 3, 4 comma 2 minus 28.28 into 10 to the power 3. 4 comma 3, they are having a two values, 28.28 into 10 to the power 3 0. 4 comma 4 28.28 into 10 to the power 3 plus 0. 4 comma 5 0. 4 comma 6 0. 5 comma 1 minus 28.28 into 10 to the power 3. 5 comma 2 28.28 into 10 to the power 3. 5 comma 3 minus 40 into 10 to the power 3. 5 comma 4 0. 5 comma 5 28.28 into 10 to the power 3 plus 40 into 10 to the power 3. They are having a two values. 5 comma 6 28.2 into 10 to the power 3 plus 0. So the minus 28.28. And then 6 comma 1 28.28 into 10 to the power 3. 6 comma 2 minus 28.28 into 10 to the power 3. 6 comma 3 0. 6 comma 4 0. 6 comma 5, they're having at minus 28.28 into 10 to the power 3 plus 0. 6 comma 6 28.28 to 10 to the power 3 plus 0. So this is the global stiffness matrix. After that, we are applying a boundary conditions. So node 1 will be fixed, so the corresponding displacements will be 0. So u2 v2 will be 0. Node 3 will be roller supports, so u v3 will be 0. And then the force acting at an node 1 at a vertical force, so f2 will be an minus 50 into 10 to the power 3. So applying this boundary conditions based on the displacement 0, so third row third column, fourth row fourth column, sixth row sixth column will be negligible. So final values we will get as an 56.569 into 10 to the power 3 0, minus 28.284 into 10 to the power 3 0, 56.569 into 10 to the power 3 28.28 into 10 to the power 3. So minus 28.284 into 10 to the power 3 28.284 into 10 to the power 3 68.28 into 10 to the power 3. A displacement of q1 q2 q5. The force of 0 minus 50 into 10 to the power 3 0. So based on these three equations, we will get the nodal displacements. So for node 1, 0.3125 mm for the horizontal displacement, and the node 1 vertical deformation minus 1.196 into in 196 mm, and then node 3 horizontal deformation will be a 0.625 mm. So thank you. We'll see you in next video. So good morning to everyone. Last videos we have discussed about the solving of Truss elements to find the displacements. Now we going to find the stresses of each elements. So formula will be E divided by L1 minus 1 1 cos theta sin theta 0 0 0 0 cos theta sin theta into nodal displacements. So for node 1, sorry, element 1, node 1 and node 2, so Q1, Q2, Q3, Q4. So Young's modulus 2 into 10 to the power 5 divided by 707.1 for a length of element 1 minus 1 1. The cos theta will be minus 0.707, sin theta minus 0.707, 0 0 0 0 minus 0.707 minus 0.707. The displacement at node 1 0.3125 and then minus 1.196 for node 2 0 0. So multiplying these values, we will get as an 199.99 199.99 minus 199.99 minus 199.99 into 0.3125 minus 1.1963 00. After multiplying this value, so 199.99 into 0.3125, 199.99 into minus 1.1963 minus 199.99 into 0 minus 199.99 into 0, the final value will be an minus 138.69 Newton per mm square. For stress at element 1 will be an minus 138.69 Newton per mm square. And then element 2, E divided by L2 minus 1 1 cos theta sin theta 0 0 0 0 cos theta sin theta Q3 Q4 Q5 Q6. So 2 into 10 to the power 5 divided by 1000 minus 1 1. So cos theta 1 sin theta 0. So 1 0 0 0 0 0 1 0 0. For displacement at node 2 0 0. For node 3 0.625 0. After multiplying this, minus 2000 0, sorry, minus 200 0 200 0. So 0 0 0.625 0. So minus 200 into 0 0 0 into 0 0 200 into 0.625 0 into 0. So the value will be 125 Newton per mm square. The stress at element 2 will be 125 Newton per mm square. Stress at element 3 E divided by L3 minus 1 1 cos theta sin theta 0 0 0 0 cos theta sin theta Q1 Q2 Q5 Q6. Here the node will be in 1 and 3. So minus, so Young's modulus will be in 2 into 10 to the power 5. Length will be in 707.1. So minus 1 1. So 0.707 cos theta sin theta minus 0.071 0 0 0 0 0.707 minus 0.707. The displacement for node 1 will be in 0.3125 minus 1.196. Node 3 0.625 0. After multiplying this, we will get as an minus 199.99 plus 199.99 199.99 minus 199.99. After multiplying this value, the stress of element 3 will be an minus 176.74 Newton per mm square. Then we want to find the reaction force. So multiplying these difference values into displacements. So minus 28.26 into 10 to the power 3 displacement of node 1, minus 28.28 into 10 to the power 3 displacement of node 2, and then node, sorry, Q1 Q2, node 2 displacement will be 0, so that will be negligible, and then minus 40 into 10 to the power 3 Q5, Q6 will be 0. So based on that we will find as an F1, and then F2 minus 28.28 into 10 to the power 3 displacement of Q1 minus 28.28 into 10 to the power 3 displacement of Q2 equal to F2. Based on this we can find as an force of reaction force of node 2. So for node 1 minus 6.136 Newton, node 2 24,993.86 Newton, and then F3 for 28.28 into 10 to the power 3 Q1 minus 28.283 10 to the power 3 Q2 minus 28.28 into 10 to the power 3 Q5 equal to F3. So that value will be an 2499.384 Newton. So finally we get as a reaction force of 49.987 into 788, where applying force will be an equal to the reaction force. So the reaction force will be a negative. So thank you. We'll see you in next video.